All right, guys, let's do an example with the Doppler shift, and I want to return to the demonstration that I did in class when I was spinning a beeper or a siren over my head. So here is the path of the siren, and it is rotating around at an angular frequency omega. And let's say that the radius of this circle r is equal to 1 meter, and that our siren emits a natural frequency of 600 hertz, kind of a low tone. And let's pick a reasonable value for me to be spinning this thing at. How about 100 revolutions per minute? And the question is, what is the difference in frequency heard by an observer as the siren is rotated? So the key physics here is that if we're an observer over here, when the siren is over here on the right-hand side of the circle, it's traveling in this direction. That's going to stretch those wavefronts out relative to the observer and decrease the frequency heard. So we hear a lower tone over here. And when the siren is over here, it is moving in this direction, it is approaching the observer, those wavefronts are going to get stacked up, and the observer will hear a higher frequency or a higher tone over here. Now, the speed that the siren is traveling depends on the radius and the angular frequency, so the velocity of the source in this case, or the speed of the source, is going to be equal to r times omega. So we do need to convert our revolutions per minute into an omega. It's worth remembering that omega is equal to 2 pi times the frequency, which is in this case going to be 2 pi times 100 cycles in 60 seconds. And so the speed of the source then, which is going away from the observer over here on the right-hand side and towards the observer over here on the left-hand side, is going to be equal to r times that angular frequency omega, which is equal to 1 meter times 2 pi radians times 100 cycles in 60 seconds. And it gives us that the speed of the source is equal to 10.5 meters per second. All right, now to figure out how the frequency is shifted, we need to use our Doppler equations for a stationary observer and a moving source. And this tells us that the Doppler shifted frequency is going to be equal to the original frequency divided by 1 plus or minus the speed of the source divided by the speed of sound. So this is plus or minus. So when the object is over here on the right-hand side and it is moving away from the observer, those wavefronts are going to stretch out. We're going to have a lower frequency. Okay, so in that case, we're going to choose the plus sign because that's going to take the original frequency and it's going to reduce it. So on the right, we hear a low tone. And the frequency is equal to that original frequency divided by 1 plus the speed of the source divided by the speed of sound, which is equal to 600 hertz divided by 1 plus 10.5 meters per second divided by 343 meters per second. And that gives us an apparent frequency or Doppler shifted frequency of 580 hertz. Alrighty, on the left, the source is approaching the observer, and we hear a high tone. And so in that case, the Doppler shifted frequency is going to be equal to the original frequency of the source over 1 minus the velocity of the source divided by the speed of sound. Okay, this is going to increase the apparent frequency, and it's important to remember whether we choose a minus or a plus sign by interpreting the physics of the problem. So that's going to give us our original 600 hertz divided by 1 minus 10.5 meters per second divided by 343 meters per second, which gives us a Doppler shifted frequency of 619 hertz. So to answer the original question, what is the difference in the frequency between one side of the circle and another? That's just 619 minus 580. So the change in the frequency from the left side of the circle to the right is 49 hertz. And that is how you do Doppler effect problems.